Okay, hi. So today I'll tell you that chiral rotation can stabilize uniaxial ordered phases in momentum-conserved fluids. Briefly, what I mean by active systems is a system in which there's a microscopic energy input, that is an energy input at the scale of particles, which can couple to the mechanics of the system in some way. And this leads to new material properties and new statistical mechanics. Briefly, why that happens is because any vectorial asymmetry in an active system can lead to motion, and any chiral asymmetry, for instance, can lead to rotation. Uh, and this leads to unusual behaviors you won't expect an equilibrium in ordered phases. And I'll talk about active uniaxial suspensions today, which are ordered phases of elongated active particles in a solvent. So first I'll tell you why achiral uniaxial phases in momentum-conserved fluids are always unstable. And then I'll tell you how chirality and chiral rotation can stabilize this instability, right? And then I'll tell you a second way that chirality can stabilize active uniaxial suspensions, which is it can stop defect separation as well, which is generic in a achiral uniaxial system, right? Okay, so I'll talk about uniaxial systems. So how do I describe those? I describe those using the order by a Q tensor, which the apolar order parameter, which can be constructed by assigning an arrow to along the long axis of every particle of your system and not caring about which direction the arrow is pointing in, right? So in this kind of system, there's no vectorial asymmetry in the base state, in the steady state. So there's no steady state flow or steady state motion. However, distortions of this can have a do have a vectorial character. They're of two different kinds in two dimension. One is distortions transverse to the ordering direction, another is distortions along the ordering direction called splay and bend. And these lead to forces and flows. So the question is, the first question to ask, and this was literally the first question that was asked in active systems, is active fluids, is how do these forces due to these vectorial asymmetries modify the phase behavior of the pneumatic, the uniaxial phase. And this was solved by Aditi Simha and Sriram Ramaswamy, and they showed that the forces due to these bend and splay fluctuations always destroy the uniaxially ordered phase. And an active force in a momentum-conserved system the vectorial asymmetry will be the divergence of a Q, which you can kind of think of as particles that pull fluid in or push fluid out through their ends. And if particles pull fluid in through their ends, then any splay distortion will lead to a disaligning torque for the particles in the middle here, destroying the ordered phase. You can show that. And if particles push fluid out through their ends, a bend distortion of this form is unstable, right? And this happens irrespective of the value of zeta and irrespective of its sign. So any sign of zeta, any value of zeta, this active force destabilizes a uniaxially ordered phase in a momentum-conserved system, right? And this has been implicated in a variety of biological, fluid dynamical systems. This is a motor microtubule system in which the oriented phase is being destabilized. This is a bacterial fluid. It's showing what is mistakenly termed as bacterial turbulence. This is another bacterial system. This is an actomycin system. This is basically a cell stuck on a substrate, and the nucleus is rotating because of the Simha-Ramaswamy instability of the cytoskeletal fluid outside the nucleus, right? So now I'll tell you how chirality can stop this from happening. So I'll talk about two-dimensional momentum-conserved films that break up-down symmetry. So you know that up from the down, right? I still have elongated particles. Now they're also chiral, so they can rotate. Each of these long particles can rotate about the z direction. I'll talk about uniaxially ordered phases still. And I'll consider every particle has the same chirality, and they rotate in the same direction with the same rotation frequency, right? Okay. And so I can write down equations of motion for these objects. So Q is the order parameter that I talked about. Even in passive systems, if I shear the fluid, it'll try to align with the flow, with the shear. That's this. In a chiral but passive system, there is an extra kind of alignment transverse to it, which is given by this. Importantly, this object makes the ordering direction rotate in time. So you can think of this as a sort of a time cholesteric. So in a cholesteric, the ordering direction rotates in space in the z direction along the pitch axis. In this kind of system, I change the pitch axis to a kind of a time axis. So the ordering direction is rotating in time, right? And so this is the most important term that I'll need. And then this is the force balance equation. This is the active, achiral active force that I already mentioned. This one is another a chiral force, which basically tells you that you have a force not only along the vector, the asymmetric vector, but also transverse to it, because I now know left from right, right? Okay, so now I'll just see how this picture transforms if each individual particle starts rotating, right? So take a system that was bent like this, and it was unstable to bend. Now rotate each of these particles by 90 degrees, you get a splayed configuration. A system in which the bend is unstable is actually, a splay will be stable. So this already hints that, this rotation can stabilize your system, and indeed that's what happens, turns out to happen. If the particle rotations are fast enough, compared to the growth rate of the Simha-Ramaswamy instability, you can stabilize your ordered phase, this rotating ordered phase. And this happens because if you look at the growth rate along all directions of the Simha-Ramaswamy instability, and if the growth rate in most directions is stabilizing, but in some directions is unstable, if you start rotating the ordering direction, you'll hit the stable directions very often in some sense. It's like, if you have a ball on a saddle, you rotate it'll normally just roll down the sides of the saddle. But if you start rotating the saddle fast enough, before it can fall down, it'll hit the stable part of the saddle and be stabilized. This is how you basically stabilize ions in traps, etc., in magnetic traps, etc., right? So that's the stabilization mechanism. It's somewhat trivial in some sense. Then in a uniaxial system, a plus half defect has a polar structure, and since everything in an active system which has a polar structure will move, a plus half defect will move. However, a minus half defect does not have a polar structure. It has a triaxial structure and it doesn't move. Since the plus half moves and the minus has a ballistic motion and minus half does not, a plus half and a minus half defect generically separate and generically destroy the ordered phase at low noise. If you have a non-rotating but chiral system, the plus half defect still has a motion, only that the direction of motion is not along the geometric polarity, but it still moves ballistically and still the plus half and the minus half separates. By measuring the difference between the geometric polarity and the direction of motion, you can actually figure out the value of the active stress, chiral active stress. But that's, however, if the particles now rotate, the direction of the defect motion rotates in time. So a plus half defect, which is away from everything else, will not move ballistically in a straight line. It will circle around. It will move in a circle. Now, if I put a minus half defect, because of the usual 1/r force between a plus half and a minus half defect, the plus half defect will actually, which would have wanted to simply move in a circle without the presence of the minus half defect, will now spiral in and hit the minus half defect without separating. So chiral rotation also stops your defects from unbinding, right? So I was talking about two-dimensional momentum conserved fluids, which is kind of difficult to realize in experiments in a sense. However, you can talk about a slightly different system, which is a layer at the interface of two three-dimensional fluids. And even in this case, Simha-Ramaswamy instability would have still operated for achiral systems with a slightly modified form of mode structure. But again, the chiral rotation in this case will stabilize the Simha-Ramaswamy instability. The mode structure becomes slightly different. It now depends linearly on the magnitude of the wave vector. The relaxation growth rate depends linearly on the magnitude of wave vector, but that's a minor difference. The mechanism still remains the same. And so basically this rotating ordered phase will have stable long range order in 2 dimensions in a momentum conserved systems, right? And this kind of a rotating phase has possibly been seen recently in experiments which are not on the interface between two fluids, but on a substrate. And if you, so this is not a very good video, but if you really stare hard at it, you can kind of see that the ordering direction is rotating in time. Possibly it's better on this. Let's see, yeah. So this is the ordering direction now, and it's slowly seeming to rotate. This is not a very good video, but Masaki Sano's group has recently obtained better videos. This is a motor microtubule system, like sulfonomy georgics. It's a minor difference, which shouldn't make things very different, but does, for reasons I don't completely understand. But Masaki Sano's group has recently observed a much more striking rotation of the ordering direction. Unfortunately, those videos are not public yet, sorry, but the paper has not been published yet, sorry. So to conclude, chirality leads to new stresses and currents, but more importantly, chiral rotation suppresses, stabilizes fluctuations, and defect suppresses defect separation. And I showed that chiral forces can be measured from the direction of the defect motion, even in systems in which there is no chiral rotation, which is true for some cell layers apparently. This I did not talk about, but even for non-rotating systems, even if your systems do not rotate, as some cell layers do, they're chiral, but they do not rotate for other reasons having to do with steric interactions. You can still have distinct flow patterns and instability, which distinct as in distinct from the Simha-Ramaswamy instability, right? And you can read about this here, and that's, thank you.
Questions?